solve the ODE. We're given an equation that might be homogeneous of degree 2. This expression y squared, if we treat this as the function m of xy, we plug in t times x comma t times y, we would just get t squared times y squared. In other words, we would have t squared times our original function, m of xy. But what about this expression here? It's not as obvious. On the one hand, we have this xy. So if we plug in t times x comma t times y, we definitely would get a t squared out of this xy part. What about this part? X times the square root of the quantity y squared minus x squared. You'll also get a t squared. But let me show that explicitly. So if this is the function n of xy, and we plug in t times x comma t times y, we would get t times x times the square root of the quantity, t squared times y squared minus t squared times x squared, and then we get a minus t squared times x times y. And we can factor that t squared under that square root, and so we have t times x times the square root of the quantity t squared, and that t squared is times the quantity y squared minus x squared. And we still have that minus t squared times x times y. Then the question is, what is the square root of t squared? Well, that's just t. Hence we have t times x times the square root of the quantity y squared minus x squared, and then we have our minus t squared times x times y. T times t obviously is just t squared, so we have t squared times x times the square root of the quantity y squared minus x squared minus t squared times x times y. We can factor that t squared, and so we have t squared times the quantity x times the square root of the quantity y squared minus x squared, and then we have our minus xy. And of course, this here is our original function, n of xy. Thus we have t squared times our original function, n of xy. This is degree 2. And likewise, if we treat y squared as the function m of xy, we plug in t times x comma t times y. That's just t squared times y squared, which is the same thing as t squared times our original function, m of xy. So this also is degree 2, so we really have a homogeneous equation. Now the question is, what do we substitute? Should we think about y in terms of the variables x and u, or should we think of the variable x in terms of the variables u and y? What's easier? Okay, so I think we're going to want to think about x in terms of the variables u and y. Then we can substitute some quantity in for dx, because otherwise we would have to substitute some quantity for dy. Then we would have this big dy quantity times this big quantity, and that's probably going to be a lot more difficult. And so we'll stipulate that x is equal to u times y. The derivative of that, via the product rule, is just dx is equal to u dy plus y du. So we'll substitute that in to our equation, and that should lead to a separable equation, and then, as long as we can integrate, we should be able to solve our differential equation. So let's substitute that in. We have y squared dx, which happens to be u dy plus y du. Then we have plus x, which is just u times y, times the square root of the quantity y squared, minus x squared, which is just u squared times y squared. And then we have a minus xy, which is just, what? U times y squared, dy, and that all equals 0. And like any good homogeneous equation, and this is of degree 2, we have this y squared, it's degree 2. We should be able to factor out a y squared with the second expression. We have y squared times the quantity u dy plus y du plus We have y squared here and a y squared here. We can factor that. So we have u times y times the square root of the quantity y squared, and that y squared is times the quantity 1 minus u squared. Okay, so minus u y squared dy, right hand side is 0. We have a y squared here, and what is the square root of y squared? Well, that's just y, so we would have y times a y. So this expression, we have a y squared. This expression, we have a y squared, so we can factor that out. Let's do that. Y squared times the quantity u dy plus y du plus y squared times the quantity u times the square root of the quantity 1 minus u squared minus u dy is equal to 0. Great. Y squared here, y squared here. We can then multiply the entire equation by y to the minus 2 power and simplify. Hence we have u dy plus y du. And let's distribute this out. Let's expand that. So we have plus u times the square root of the quantity 1 minus u squared dy minus a u dy is equal to 0. We have a positive u dy. We have a negative u dy. So that's nice. That goes away. And now we have y du plus u times the square root of the quantity 1 minus u squared dy is equal to 0. Let's subtract y du from both the left hand and right hand side of our equation. Hence we have u times the square root of the quantity 1 minus u squared dy is equal to minus y du. And then through division we can separate our variables. We'll divide both sides by y. Actually, let's do it by minus y. I think that'll be a little easier. And we'll divide both sides by u times the square root of the quantity 1 minus u squared. Now let's simplify. The left-hand side is just minus dy over y. The right-hand side is du over u times the square root of the quantity 1 minus u squared. Our y variables are on the left-hand side. All our u variables are on the right-hand side, so we can anti-differentiate. The left-hand side is pretty easy. The right-hand side is not so easy. There's no obvious substitution we can do there. However, a trigonometric substitution should be possible because the square root of the quantity 1 minus u squared, that's very trigonometric-like. So let's model this with a right triangle. So this is supposed to be a right angle there. This is theta. Of course, we have the Pythagorean theorem, a squared plus b squared equals c squared. I think we should use this leg to represent the square root of the quantity 1 minus u squared. And then if this is u and this is 1, those sides are consistent with the Pythagorean theorem. And of course, note, so cotoa, cosecant, secant, cotangent. So what can we do here? What's the sine of theta? Well, the sine of theta is opposite over hypotenuse to our angle theta, right? So u is just the sine of theta, and that looks pretty good. The derivative of that is just du is equal to cosine of theta d theta, and now we can do some substitutions here. So we have du, which is just the cosine of theta d theta. We have u, which is the sine of theta. Then we have that multiplied by the square root of the quantity, 1 minus u squared. So that's sine squared of theta. We also know, of course, that the sine squared of theta plus the cosine squared of theta is equal to 1. That's just the Pythagorean theorem. So if we have 1 minus the sine squared of theta, that's just the cosine squared of theta. So now we have cosine of theta d theta over the sine of theta times the square root of the cosine squared of theta. Well, the cosine squared of theta is just the cosine of theta. So we have cosine theta d theta, sine of theta, cosine of theta? Well, the cosine of thetas, those just drop out, they simplify. So now we have the indefinite integral d theta over the sine of theta, which is just the cosecant of theta d theta. And what is that? That would be minus natural logarithm of the absolute value of the quantity, the cosecant of theta, and that's plus the cotangent of theta. Alright. We're in this theta land. We want to return back to the u land. So the question is, what is the cosecant of theta? So given this right triangle, so the cosecant is just the hypotenuse over opposite. So we have 1 over u. So we have minus natural logarithm of the absolute value of the quantity 1 over u. And what is the cotangent of theta? So that would just be the adjacent over the opposite. So we have a plus the square root of the quantity 1 minus u squared over u. And of course these have the same common denominator, so that's just minus natural logarithm of the absolute value of the quantity 1 plus the square root of the quantity 1 minus u squared over u. So this here is our right hand side. So we figured that out. What about this left hand side? So that would just be minus natural logarithm of the absolute value of y. So let's put this together. So we have minus natural logarithm of the absolute value of y is equal to minus natural logarithm of the absolute value of the quantity 1 plus the square root of the quantity 1 minus u squared over u, and we'll add our arbitrary constant. And to simplify this a little bit more, we will multiply this entire equation by minus 1. So now we have this. Okay. Our constant changed technically, so I'll call that C naught. And before we substitute for u, let's just simplify this a little bit more. We'll use our various properties of logarithms, of exponents. So we have e, we can raise this to the following power, and likewise for this right hand side. We have inverses. The left hand side is just the absolute value of y. The right hand side could be expanded out to this times e to the c naught power. That's just an arbitrary constant. So now we have this. So we have c, so our arbitrary constant, times the quantity 1 plus the square root of the quantity 1 minus u squared over u. Now note, of course, that x is equal to u times y. That means that u must be x over y. So let's plug that in. And I should have this in absolute values. Sorry. However, I can actually drop the absolute value signs here because the plus and minus, so to speak, can be absorbed into our arbitrary constant. So we're good to go, actually. So now we have y is equal to c times this quantity. So u squared, so this is x squared over y squared. And here we have x over y. And let's simplify this a little bit. There are different ways, I guess, to look at that. One way is to think of it this way. Let me just write this out again. So we have this, and this is divided by x over y, but that's the same thing as multiplied by y over x, right? And so we have y equal to c times this quantity, so we have y plus y times the square root of the quantity 1 minus x squared over y squared over x. This is not a horrible answer. However, we can make this look a little better. So here we have the square root of this quantity. But remember, we started out with this right here. We have the square root of the quantity y squared minus x squared. We can re-express that just doing a little bit of algebra. Okay, so I think that actually would be a good idea, because this y, so to speak, we can think of that as factored out of the square root quantity. So we can think of it this way: there's a y squared in that square root of quantity, so to speak. So we have y is equal to c times the quantity y plus the square root of the quantity y squared minus, well, x squared over y squared. That multiplied by y squared is just x squared. So that's pretty good. So here we have something approaching what we want, but let's make this a little bit nicer. Let's multiply this entire equation by x. So now we have y times x is equal to c times this quantity, y plus the square root of the quantity y squared minus x squared. And this, I think, is a really good answer. Of course, y squared should be greater than x squared, but in any case, this will be our final answer. Y times x is equal to c times the quantity y plus the square root of the quantity y squared minus x squared. That is our solution.